front of the hotel. And it's also okay to spill out of that area into the restaurant and sort of the front hotel of the area. Starting tomorrow, we're going to be in salons A, B, and C, which are sort of a conference center that are in back of the hotel. You sort of go out of the hotel to the back, and then sort of outside and then inside again. There's a wedding in there tonight, so that's why we don't have that room for tonight. But anyway. What time do the work? They begin at 7 every night. Yeah. So anyway, our last speaker of the morning is Matt Baker from Georgia Tech.
All right, so thanks very much to the organizers for inviting me. It's a real honor to be here and a pleasure to be able to give a series of lectures for you. So what I'm going to tell you about is, first of all, the rudiments of Berkovich's theory of analytic spaces, but really only in some very special cases and focusing on examples and intuition and not focusing so much on the general theory, but Brian, in his last couple of lectures, will tell you more about the general theory of Berkovich spaces as it would be derived analogously to the theory of rigid spaces. So what I want to do today is just give you some intuition about what's going on. The idea is somehow that you take a classical rigid space and add many new points to it in order to remedy this defect of connectedness, which Brian talked about, and also to remedy the lack of compactness. So you can get spaces that are connected and compact by adding in many new points, and I want to sort of explain today what those new points are. And I will also be talking about potential theory, which, well, I don't want to define what that means right now, but you'll see later what I have in mind. So let me just start at the beginning by sketching out my goals in a more detailed way. So what we'll do is we'll describe in detail the structure of Berkovich analytic curves, and with a particular emphasis on the Berkovich projective line. So in some sense, the simplest Berkovich space would be the projective line, or we'll also talk about the affine line and the unit disk, etc. But in the last lecture, I'll say some more things about general curves. And in particular, I'll talk about potential theory. And roughly, this means, the theory of Laplacian's harmonic and subharmonic functions. So very classical things that you have over the complex numbers, which in fact have very precise and beautiful p-adic analogs that have been discovered recently by several people independently in various levels of generality and with different kinds of applications in mind. But I'll try to sketch out the basics of this theory. And then one ultimate goal, which actually I'm not going to say anything about. I thought originally maybe I would say something about this, but it turned out to be too ambitious. But the idea you should keep in mind is that we would really like, in an ideal world, to treat Archimedean and non-Archimedean geometry in exactly the same way, and just say that anything you do over the complex numbers has some analog over the p-adic numbers and vice versa. That's not literally true, of course. There are differences between the theories, but Berkovich's theory will make this much more plausible that such a thing might be possible than the theory of rigid analytic spaces maybe would lead you to believe, and certainly more than the naive theory of totally disconnected topology of a k-analytic manifold would lead you to believe. And then there's also this connection with Arakelov's analogy that if you know anything about Arakelov theory, which I won't really discuss, you do two different things. You do intersection theory at finite places on some model for your scheme. So maybe on an arithmetic surface, whose generic fiber is some curve over a number field, say, then you do arithmetic intersection theory on some model for your curve. And the analogous thing that you do at infinite places is potential theory on the corresponding Riemann surface, so using Green's functions. And these Green's functions are somehow analogous, from Arakelov's point of view, to intersection forms. But it seems just like a formal analogy until you delve into this theory of Berkovich spaces, in which it becomes quite precise. I mean, literally, the Green's functions in the potential theoretic context on Berkovich space are computing intersections on models in some very nice way that takes different models into account at the same time. And so, well, I want to start in a much more elementary way than this, but ultimately this is where such a theory can lead to really understand Arakelov theory in a more conceptual way and in a more symmetric way at all places. And Thuillier, a student of Chambers-Loire, has really laid out the foundations for curves in his recent PhD thesis of how to do Arakelov theory in a symmetric way at all places. But I won't really discuss that aspect of his theory. So credits for this material, I mean, there's a lot of different people that have worked on this, and it would be too complicated to try to explain who did what, when, and in what order. So rather, I'll just name some people, and you can see the notes for a little bit more information. I should say that the lecture notes, which I've written up, have almost everything that I'm going to say in them. And also, I've put these slides up on my website, and they may be soon on the Arizona Winter School site. So it's not necessary to take notes unless you really want to. So among the people that have contributed to this subject, well, we've got Vladimir Berkovich, who really introduced these spaces. Actually, the physical spaces that, as topological spaces that I'll be talking about, were introduced even before Berkovich by various people in the French school. But I think the idea of treating them in a manner completely analogous to rigid analytic geometry or to scheme theory was due to Berkovich, and he has proved a tremendous number of powerful results along these lines. So that's certainly the main person I should mention is Berkovich. I wrote a manuscript that's still in progress with Robert Rumley, which gives a lot of the proofs and details behind many of the theorems that I'll state without proof in my talks. Chambers-Loire, I mentioned, has, and his student Thuillier have done a lot of work in this direction, much more general than the things that Rumley and I did. So they apply more generally over more general ground fields and to more general spaces. Juan Rivera-Letelier actually does p-adic dynamics and was a student of Yoko's, and he actually independently discovered Berkovich space because he was thinking about p-adic dynamics and realized that this was the perfect tool you needed to prove interesting things about p-adic dynamics that aren't accessible from the classical point of view. So he, in fact, rediscovered several of the things that I'll mention by himself and talked about this hyperbolic space, which I'll define later. But turns out it's part of Berkovich's theory, really. And then Favre and Johnson have written a book called The Valuative Tree and several papers in which they lay out a theory of Laplacians on real trees, which in the case of the Berkovich projective line coincides with the definitions that I'll give here of the Laplacian operator on Berkovich projective line. And so their theory is closely related, and many of the results that I'll state can be deduced from their theory too, but they have applications actually to complex dynamics in mind. So it turns out you can not only study p-adic things using Berkovich's theory, but even Archimedean things, because it applies over any complete valued field. And so in particular, you could take Laurent series over the field of complex numbers and put a non-Archimedean valuation on that in the usual way. And then take the completed algebraic closure and work over this kind of field and view this as telling you something about families or infinitesimal families of complex varieties or complex analytic spaces. And so, in fact, you can do things, you can get Archimedean results from this theory as well. Right, and there's many more people that have worked on related things, but I think I should move on. So, as I said, I won't be too specific about who proved what in these talks. All right, now notation-wise, very important convention that I'll just lay out from the beginning and I'll repeat in every one of my talks is that my ground field K is going to be an algebraically closed field, which is complete with respect to some non-trivial, non-Archimedean absolute value. So if you want to have a very concrete thing to keep in mind, you can imagine that K is the field CP that Brian defined in his talk. And but it could also be one of these Laurent series over the complex number type fields that I just mentioned, or there are other examples as well. Algebraically closed is not crucial for the development of Berkovich's theory, and I'm sure Brian will do it over more general ground fields, but in terms of visualizing what these spaces look like, and in terms of making precise some of the theorems, I want to say it's very convenient to always work over an algebraically closed field. I mean, it's as if we want to understand what the analog of a complex manifold is in the p-adic world. And so I don't want to talk about real manifolds and all the complications that would involve. So I will stick to the sort of algebraically closed case where you really have more geometric intuition. Characteristic is not important. So characteristic P is fine. K tilde will be the residue field of K, which will show up today in several places. And just my notation for disks will be that, so this B of AR here will denote the closed disk of radius R centered at A. And I'm allowing any positive real number. So that's different from in Brian's talk, where R had to be in the value group in order to define a Weierstrass domain of the unit disk. But in Berkovich's theory, you can allow an arbitrary positive radius. And actually, I will sometimes include the degenerate case where R is 0 as well, and think of points as disks of radius 0. And then, so I'll distinguish sometimes between rational and irrational disks. And if I write B of AR minus, that will be the open disk of radius R centered at A. Okay, now the usual topology on K is totally disconnected and it's not locally compact. Right? So these are two basic deficiencies of working with the natural topology on K, which have to be corrected if you want a geometrically satisfying theory. You want to do things like analytic continuation, and many other constructions are just much less intuitive and much harder to make rigorous over fields like with this kind of topology. So Tate's solution, as Brian discussed, was to develop this theory of rigid analysis where you introduce a certain Grothendieck topology on K, or on the points of some rigid variety over K. And this does actually allow you to do work with sheaves of analytic functions and to do analytic continuation to recover connectedness properties. So it's a beautiful theory with many applications, and it's quite natural. But the thing is that you have to keep in mind is that you haven't actually changed the topological space, so to speak. You've introduced this Grothendieck topology, but in terms of actual topological spaces, you haven't done anything any different. The only physical topological space that you have in rigid analysis is the one you started with, which is totally disconnected. In Berkovich's theory, you actually introduce many new points in order to get a space. So for example, the Berkovich affine line over K is locally compact. It's Hausdorff. And it's not only connected, but it's actually path connected. You can draw real arcs between any 2 points. And it's uniquely path connected. There's a unique such arc between any 2 points. And K, with its usual disconnected topology, is a dense subspace of the Berkovich projective line. So you've somehow compactified, well, the A1 is locally compact. P1, if you add an extra point at infinity, you get a compact space which contains the projective line over K as a dense subspace. And so you've not only recovered some connectedness property from starting with a totally disconnected space, but you actually have a uniquely path-connected space. It's even better than what you might have hoped for. So what I'll explain is an elementary way to construct this space, A1 Berk. That's in this lecture. I'll explain how to give a very elementary construction of this space and to see what it looks like and how you can think about it in a sort of very intuitive way. Excuse me. All right. And what I will talk about later, maybe starting in the second lecture, is that this Berkovich projective line can somehow be thought of as a profinite R tree, whatever that means. I'll define that later. But this allows one to construct a Laplacian operator, which ultimately is derived from the Laplacian on a finite graph. So there's a very classical notion of a Laplacian on a graph, which is a kind of combinatorial version of the Laplacian in R2, say, or on the real line, by which you can define harmonic functions and prove various properties that they have. And so somehow this tree structure on Berkovich space is what's behind the existence of a good Laplacian operator. And then once you have this Laplacian, you can talk about harmonic functions, subharmonic functions, Green's functions, and various other things. For example, as come up in Arakelov theory, you need these Arakelov-Green functions. So you can make good sense of that once you have this Laplacian. And it really parallels the classical theory. So we'll see a maximum modulus principle analogous to the one for harmonic functions in the complex plane, and various other analogs of the Poisson formula and other things. So that's what's coming up. But I want to start sort of in a more elementary level now and just tell you how Berkovich defines his spaces in terms of multiplicative seminorms, and then shortly I'll give you the intuition for where this comes from. So let me just give you a definition, and then we'll see how you might come up with such a definition. So a multiplicative seminorm on a ring A is just some function which I'll write as absolute value sub x to the non-negative reals satisfying certain obvious axioms. So you've got the absolute value of 0 is 0, the absolute value of 1 is 1. The absolute value of a product is the product of the absolute values, so that would be the difference. Well, that's what the word multiplicative refers to. And as Brian mentioned in his lectures, the Gauss norm on this Tate algebra and on the Tate algebra in general is multiplicative. So that's an example. An example of such a multiplicative seminorm on a ring A would be look at the Tate algebra Tn and take the Gauss norm. And I want to require that it satisfies the triangle inequality. Now here I've written the usual triangle inequality, but we will quickly specialize to the non-Archimedean case where all of the seminorms will actually satisfy the stronger ultrametric version of this. But at first, it's convenient to allow these Archimedean seminorms as well. But my field K is non-Archimedean, remember. And as a set, I want to define the Berkovich affine line to consist of all multiplicative seminorms on this polynomial ring K adjoin T, which extend the usual absolute value on K. And I will give several examples of this. Now, if I wanted to define the Berkovich unit disk, I would replace this polynomial ring K adjoin T by the Tate algebra in one variable. So I'd look at restricted power series rings, and then the same definition would recover the Berkovich unit disk inside of here. But I want to define Berkovich affine space directly in terms of polynomial rings, which is just a different approach. So some remarks to keep in mind. First of all, throughout, I'm reminding you again that I'm assuming the field is algebraically closed. But for that definition, it's not necessary. You could make that definition without assuming K is algebraically closed. And for these psychological reasons, I will identify a semi-norm with a point of the space and usually write x rather than absolute value sub x. And if we wanted to think of it as a maximal ideal in the ring, then I could write m sub x. But these don't in general come from maximal ideals in the polynomial ring, so I won't use that notation very often. And I'll typically omit reference to the ground field, which will just be somehow fixed throughout. So I'll just write A1 Berk and suppress the dependence on the field K. All right, so I just told you a set. I defined a set, some multiplicative seminorms on a certain polynomial ring. So the topology on this set is the weakest one for which these maps are all continuous. So for any polynomial f, the map that sends a point to the absolute value of f with respect to that point, that should always be continuous. All right, so what does that mean slightly more concretely? So for example, a fundamental system of open neighborhoods for this topology would be given by looking at the set of points where the absolute value of some polynomial is between alpha and beta, and you do that for some finite set of polynomials. And that will define certain subsets of A1 Berk, which you call basic open sets. And this will be made more explicit soon. I mean, it's still hard to visualize what that means, probably. But one thing to point out, it's not completely obvious, I think, but if you restrict to K, well, I'll say how K sits inside A1 Berk in just a second, but this restricts to canonical topology as Brian just defined it on K. So this is compatible with things from rigid analysis. Now, you can motivate this definition in the following way. So first of all, in the Archimedean case, and this is why I wanted to allow this more general triangle inequality, just so I could say something about the Archimedean case. In the Archimedean case, every multiplicative seminorm on this polynomial ring, which extends the usual absolute value on C, just comes from evaluating at a point. So it's just of the form f goes to absolute value f of z for some complex number z. And this follows from results, classical results in functional analysis. And so in some sense, this corresponding Berkovich space over C, the Berkovich affine line over C is just C. And so on the one hand, it means there's really no point in introducing any new terminology here in the case of the complex numbers. But it's psychologically very useful to realize that you have a definition of a space which over the complex numbers recovers the usual affine line over C, as not as a scheme, but as a topological space anyway. And then but when you do the same definition in the non-Archimedean case, you get many more points. So when K is non-Archimedean, there are many more points than just evaluation of a polynomial at a point and then taking absolute values. And for example, well, Brian already discussed this example in his talk. The sup norm on a disk is multiplicative. Right? So if I take a closed disk of radius r, and I define a corresponding seminorm to be the sup, which is also the max, over all points in the disk of the absolute value of f of z, then this is actually multiplicative. Right? And so this is from Gauss's lemma in algebra, hence the name Gauss norm, as was discussed. And but somehow this has no Archimedean analog, right? The sup norm on a disk over C is certainly not multiplicative. It's some special property of the ultrametric inequality. And so this gives a whole new collection of points that we've added to our space. Not only does every point of K, every element of our field K gives rise to a point, namely a multiplicative seminorm, but in fact every closed disk gives rise to a point, right? Oh, yeah. When I said equal to the max, that was for R in the value group and the multiplicativity as well. Yeah. So this is slightly more general, right? But it's still true that this sup norm, even if R is not in the value group of K, it's still multiplicative. And the set of all, so possibly degenerate radius 0 disks, therefore embeds into this Berkovich space. Well, I guess maybe there's some argument needed there to show that that map is injective, but it's easy. So, so in particular, K sits inside of Berkovich space as this sort of degenerate disks of radius 0. And with that topology that I just defined, it's an exercise to show that K is dense. So that will be, I don't have a formal exercise work group, but if I did, that would be the first exercise maybe. And similarly, the projective line over K can be naturally embedded as a dense subset of P1 Berk. So for now, P1 Berk is just add a point at infinity to the Berkovich affine line and give it the topology of the one-point compactification. But this is sort of not a very good way to generalize to higher dimensions, so I'll give a more natural definition of P1 in the next lecture. But I want to describe now why, at least intuitively, why this space A1 Berk is uniquely path connected. Are there any, before I start this, are there any questions so far? Yes?
Are you leaving out
Well, I'm getting to that, yeah. So there's a complete classification of what all these points look like, and we'll be able to visualize it quite concretely. But there's still lots more left. So I haven't told you all the points yet. Any other questions? Okay. So, all right, so suppose, right now I just want to tell you how to draw paths between things in K. Because, I mean, after all, what we're really interested in is maybe the underlying classical rigid space, the affine line over K, just in the usual pre-Berkovich sense. But if we take 2 points of K, how do we connect them up with a path? Well, this is very easy given the description I've just told you. So here's what you do. So you think of A as a degenerate disk of radius 0, and you start taking disks around A of larger and larger radius. Okay? And then keep going, keep increasing the radius until you have a disk that also contains A prime. Now, actually, the magic of non-Archimedean land is that it's somehow, this is symmetric in A and A prime, right? So had I done the same thing with A prime and increased the radius till I got to A, I would end up with the same disk. Because another way to think about this is you take 2 families of disks starting at A and A prime. You gradually let the radii grow, and they stay disjoint until suddenly they morph into one disk. And this is a simple consequence of the fact that in non-Archimedean geometry, 2 disks are either disjoint or one contains the other, right? And so it's easy to see if you are familiar with that fact, which I hope you all are, then it's easy to see that what I just said is correct. And so, so that's the path somehow. That I just described a path of disks. You increase around A till you have this disk that also contains A prime. You can recenter that disk at A prime, and now you decrease towards the center A prime until you get down to radius 0. And I've just described a collection of disks. And it turns out so that's some subset of the Berkovich affine line. And it turns out that in this topology that I defined, this is homeomorphic to an interval. So, I mean, this is actually a continuous path in the Berkovich space with that topology that I described. And so in this way, we've connected up this totally disconnected space K by adding points which correspond to disks. So, I mean, this unique path connectedness is actually very, very, very simple concept. And it's so elementary and natural that it's rather surprising that this is a somewhat recent theory. I mean, okay, well, maybe I'll say some more philosophical remarks later about that. As I said, there were people that did discover these sorts of things before Berkovich, just nobody made it into a systematic theory before him. But back to this question that was raised of whether we've found all such multiplicative seminorms, we haven't yet described all such seminorms. And if you want a compact space out of this construction, or a locally compact space if you're talking about A1, then you have to add even more points. I mean, I say usually because it depends what the field K is. But for example, if K is equal to CP, the completion of an algebraic closure of QP, then the field CP has this property that it's not spherically complete. To be not spherically complete, I should have actually highlighted the word blue because I'm defining what it means to be not spherically complete. So it means that there are decreasing sequences of closed disks with empty intersection. Now, from a very naive point of view, that might be surprising because there's the fact that a nested intersection of compact sets is always non-empty. But these aren't compact, right? A disk, closed disk in CP is not compact. For example, the different residue classes, all the different inverse images of reductions in FP bar form an open cover with no finite subcover. So whenever K has infinite residue field, which is the case automatically since I'm assuming that K is algebraically closed, you're going to run into this potential problem that you can have failure of local compactness on your field K, and then you may run into this problem about decreasing sequences of disks having empty intersection. Now, why is this? Why do we need to do something about this? Why do we care? Well, we actually have to add such points to our space in order to account for such sequences, because if I take, rigorously speaking, if I have a nested sequence of closed disks and I take the limit of the sup norms, that will be a multiplicative semi-norm, which extends the absolute value on k. That's almost immediate from the definitions. And so at least according to Berkovich's definition of the space of all multiplicative semi-norms, we need to include these points. But intuitively, we also need to include them because if you have this family of decreasing family of closed disks, each one corresponds to a point of Berkovich space, and they're somehow converging, but there's no limit there, right? Because there's no disk that they're going down to. And so, if we want to have a compact space, we have to add somehow endpoints that correspond to these funny kind of sequences. So that's what we do. We just add in 1 point for each such sequence. Well, not quite, because you might have cofinal, right? You might have two nested sequences of which would somehow, well, of course they have the same intersection because the intersections are both empty, but so that's not a good way to define what we mean by this cofinality, but just well, you can imagine what I mean. I don't want to give rigorous definition. But if you have two sequences of disks with empty intersection, there's a natural equivalence relation, and they will determine the same semi-norm if these two sequences are cofinal. So now, according to a result of Berkovich, we've now described all points of the Berkovich affine line. So all multiplicative semi-norms extending the usual norm on K fall into this classification scheme. So here's what I call Berkovich's classification theorem. So every point of Berkovich space corresponds to such a nested sequence of closed disks with either empty or non-empty intersection, in the sense that every such semi-norm, every multiplicative semi-norm on this polynomial ring is a limit of semi-norms from just limit of sup norms on disks. Now this includes all the cases I've talked about, right? Because evaluation at a point, you just think of a nested sequence of closed disks whose intersections are that point. And then evaluation at that point comes from the sup norms on this decreasing sequence of disks. And if I have just the sup norm on a disk itself, take a constant sequence here. In this way, you get every point. And then we know also when they define the same point, either each has a non-empty intersections and the intersections are the same, or they both have empty intersection and the two sequences are cofinal. So if you put this equivalence relation on nested sequences of closed disks, you get everything. This is not hard to prove, but I'm not going to give the proof. I think it's much more important when starting out in this subject to realize that this is one of the few cases where we really can completely classify all points of the space in a totally explicit way. And my main reason for focusing throughout these talks on the case of the affine or projective lines is mainly because you can really understand what these points correspond to in a very concrete way, and it gives you some very elementary tools for doing some fairly sophisticated things. And then in order to generalize to more general Berkovich spaces, you necessarily need to introduce a lot more machinery, so I'll save that until the very end of my talks when Brian has introduced some more machinery by that time as well. So it's useful to categorize these points into 4 types according to the nature of the intersection. I mean, it's somewhat artificial classification, but it's very useful classification, and I will refer to this throughout, so try to remember what these names mean if possible. I'll try to keep reminding you, but at some point I'll probably just start using this language without reminding you anymore. So type 1 is just the intersection is a point. So these are the classical points that we started with. Just elements of K are the type 1 points. And those sit densely inside of the Berkovich affine line. And so those I'll call the points of type 1. It's not me. Berkovich calls these points of type 1. This is his terminology. If B is a closed disk with radius belonging to the value group, that's type 2. So those are the familiar points from rigid analysis that give you these Gauss norms. Now you've got these new kind of points where you have irrational disks, disks whose radius is not in the value group, but you can still consider the soup on such a disk. Now, the soup is not attained because there's somehow intuitively nothing on the boundary of such a disk. So you can't really expect the soup to be attained by a point of the space, but it does give you a semi-norm, and certainly if you want connectedness, you have to include such things. I mean, this unique path between 2 points that I described clearly has to go through disks of irrational as well as rational radius. So you definitely want these points. And the type 4 points are the hardest ones to visualize. Those are where the intersection is empty. And there are uncountably many such points, and they're definitely harder to think about, but somehow they're not actually necessary for an intuitive understanding of the structure of the Berkovich affine and projective lines. I mean, if you basically ignore the points of type 4, well, you won't have a compact space because you'll be missing certain endpoints of this tree that I'm about to draw. But paths between points of type 1 through type 3 don't actually go through type 4 points. So the space, the complement of the space of type 4 points is connected. It's a simpler way of saying what I just said. And it has many nice properties that you can really visualize. Points of type 1 through 3 are just the disks, including disks of radius 0 and disks of irrational radius. And we can all visualize that. Type 4 points are a bit harder to understand. That's correct. So over a spherically complete field K, you don't have any points of type 4. And then this description, in terms of disks is really is precise. So yeah, another alternative for those of you that can't visualize the type 4 points is if you can actually visualize a spherically complete field, then you're done. You don't even have to worry about points of type 4 at all. And so there's this field usually called omega p in p-adic analysis, which is the smallest spherically complete extension of QP. But most of the definitions that I've seen involve ultrafilters, and I mean, it's not exactly any easier to visualize what it means than it is to just talk about points of type 4 as I'm doing. Okay. What's that? Okay, well, so you can ask Bjorn if you want to visualize points of type 4. All right, so I'm going to introduce notation that's not standard in the literature, but I'm just making it up here. Zeta AR will be the point of type 2 or 3, which corresponds to the disk of radius r around A. And so following some fairly evident terminology that was suggested by Chambers-Loire, the point corresponding to the unit disk will be called the Gauss point, because that corresponds to the Gauss norm in the sense of the maximum of the coefficients as Brian defined it. I mean, here I'm doing polynomials, but it's roughly the same idea. So we have this sort of distinguished point called the Gauss point, which I'll come to later. All right, so here's a picture of Berkovich space. Now, it's rather hard to draw the whole thing, so I've just selected a small piece of Berkovich space to sketch for you. This picture actually was done by Joe Silverman, who's writing a book on arithmetic dynamics and is including a chapter about dynamics on Berkovich space. So he drew this picture, and it was much better than anything I could come up with using a computer, so I borrowed it. So here's the Gauss point, right? That's corresponding to the unit disk. We've got the point 0, the type 1 point, the classical point we started with down here, say, and the point infinity up there. And here's the path from 0 to infinity goes through the Gauss point. And what is that path? This is just start at 0, take disks of increasing radius, right, bigger and bigger and bigger. And when the radius goes to infinity, somehow that limits up in this point at infinity up here that I've added on. And if I had the point, I don't know, 1 in my field K, that might be here. And then the path between 0 and 1, right, in order to link up 0 and 1 by a path, you basically have to go up to the unit disk, right? The smallest disk containing 0 and 1 is, this is another exercise simpler than the other ones that I've given, is the unit disk. And so the first place where these points will link up is at the Gauss point. So these paths are really just chains of disks. They're families of closed disks. And now the type 4 points you can think of as they should actually be further up. I meant to tell Joe that he should modify his picture a little bit. These points, which are the type 4 points, somehow should be thought of as higher up than these, for the simple reason that a nested family of closed disks with empty intersection, necessarily the radii go to some real number r, which is strictly positive. That's just because k is complete, right? If you had the radii going to 0, there actually would be a point in the intersection by completeness. And so somehow the radius of a type 4 point is strictly positive, and what I'm drawing down here are the points of sort of radius 0. So now the thing you have to keep in mind about this picture is it's drastically incomplete in the sense that I've drawn some wild branching here, but it's much worse than this. Every time you see branching, you actually have infinitely many branches coming out. And each of those branches splits into infinitely many more branches along a dense set of points along each segment. So each time you have a segment, you have a dense set of points at which it branches into infinitely many new segments. And you iterate this infinitely many times. And the cardinalities of these infinite sets depend on the size of the field K, but they could even be uncountable. So if your field is omega p, this spherically complete field, then you'd actually have an uncountable set of branches at not just a dense set of points, but at every point. So on the one hand, it looks impossible to visualize when you think of it that way. Of course, if you leave out enough branching, then you start to think you could visualize this space. You just don't draw how horrible it really is. But at the same time, what I'd like to convince you of is that really the way, if you want to understand this space on an intuitive level, you should think of it as being built up out of finite trees. So particularly, I'll discuss in the next lecture how you can naturally think of this as an inverse limit of finite trees. And that is now a much easier thing to grasp and tells you both about the topology and the general structure of these spaces. So here's another picture. So I told you that Berkovich spaces were discovered before Berkovich by the French school. So this, if my history is correct, Antoine de Saint-Exupéry was the first person to draw a picture of the Berkovich projective line. So this is the Gauss point right here. The little prince is standing on the Gauss point, and in fact, this actually brings me to my next topic, which is if you're standing at the Gauss point and looking out, what do you see? So I thank the author of The Little Prince for this very suggestive picture. So the next question will be, what would you see if you were the little prince standing at the Gauss point and looking out? What are the different directions in which you can look? Okay, well, I'm going to summarize the comments I made before. There's branching only at the points of type 2, not at the points of type 3, which may be not completely obvious, but I hope to explain why that's true. And some of the branches extend all the way to the bottom, terminating in points of type 1, and others are sort of cauterized off earlier. Those were those open circles you saw, and they end at points of type 4. But every branch does eventually end in some endpoint, and that's related to the fact that the space is compact. Okay, so now I want to talk about the space of tangent directions at a given point, and that's what I was saying. If you're standing at a point of Berkovich space and looking around, what can you see? So I'll write T sub x for the space of tangent directions. If it's really like a projectivized tangent space, because I don't have magnitudes to these vectors, but the space of tangent directions are just the equivalence class of paths emanating from x, where two paths are equivalent if they share a common initial segment. So this should be a sort of familiar definition of a tangent direction. And another way to define it in this case is that you can think of tangent directions as connected components of the complement of x, right? So if I remove that Gauss point, say, it will break up the tree into an infinite set of components, and each of those components is a direction in which I could have gone. So the connected components of the complement are in one-to-one correspondence with these tangent directions. And I'm going to write UXV for the connected component of the complement corresponding to a tangent vector V. So these are all points that the little prince can see by looking in some particular direction. And I'll draw a picture of that in a minute, but these open sets actually generate the topology in the sense they form a subbase for the topology. So if you take finite intersections of these open sets, you'll get a neighborhood base for the topology on Berkovich space. And what that suggests is there's a paper on R trees where they I have terminology that I like. They call it the observer's topology. So what this topology is, in terms of this tree structure, is you place a finite set of observers at finitely many points on the tree, and they each pick a direction in which to look. And the set of points they can all simultaneously see, that's an intersection of sets of this form, and so that's a basic open set in this topology. So the basic open neighborhoods of points of Berkovich space are the set of points which a finite set of observers can simultaneously see. And so the simplest kind of such sets are Berkovich disks. So this is just the obvious generalization of a disk to Berkovich space. Namely, I can just look at, I keep forgetting which hand is which, the set of points x so that the absolute value of t minus a sub x is less than or equal to r. Sorry, less than r for an open disk and less than or equal to r for a closed disk. So clearly, if I intersect with k, I just get the usual notion of a disk. But this actually makes sense in Berkovich space. So I'll call these open Berkovich disks or closed Berkovich disks. And once we start working more with the projective line, the complement in the projective line of an open disk should be thought of as a closed disk. So, maybe centered at infinity. And so I'll allow, when I talk about open and closed Berkovich disks in P1, I'll include such things as well. Complement of an open Berkovich disk in A1 will be a closed Berkovich disk in P1. And this is what I said, that the intersection of a Berkovich open disk with P1 of k is just a classical open disk. So here's, see, when I don't know, I'm not very good at drawing with this LaTeX plotting command, so I just drew something myself here. So that's a picture of a Berkovich open disk. And it's actually one of these sets U of xv, right? If you're standing at the Gauss point looking in this direction, these are all the points you can see. You should think of what's going on here as these all start out, all these paths share a common initial segment. It's just so close to the Gauss point that you can't see it in the way I've drawn it. But those all lie in one particular tangent direction. And the other points are in some different direction. And so the lemma is that every open set UXV, set of all points you can see looking in a certain direction, with x of type 2 or type 3, namely corresponding to an actual disk, is a Berkovich open disk, and conversely. So this abstract description of Berkovich disks in terms of absolute value of t minus a is less than r. In terms of the tree topology, this just means the set of all points you can see looking in some direction. And finite intersections of Berkovich disks are what I'll call open disks, or what I'll call simple domains. And as I mentioned, they form a neighborhood base for the topology. And if you have a simple domain, it will have a finite set of boundary points. Those are the points where the observers are standing. And a finite set of tangent vectors, inward pointing tangent vectors, which I'll call the ends. And so that looks something like this. These are the 3 boundary points of a simple domain. And then there's 3 inward pointing tangent directions, which I'll refer to as the ends. And you should think of this is like you take, say, this big open disk, and you remove everything down here is a closed disk, and everything that was below here is a closed disk. So you've taken a big open disk, and you've removed 2 closed disks from it. And so what you have is sort of the analog of an open aphanoid in the terminology of rigid analysis. Yes. So if this point, say, corresponds to some, say, the Gauss point, the unit disk, then everything below that in the direction of 0 is the open unit disk. And everything above x2 might correspond to some disk of radius r, which is strictly less than 1. And so everything above that will be the complement of a closed disk of radius r. And here will be some other closed disk that we've removed. So we've taken a big open disk, which you think of as everything in this direction from the Gauss point. And then we've removed a closed disk here and a closed disk here. So we're left with everything that's above, outside of those two closed disks, but inside of the big open disk. And what you see is there's a tree here going from there to there to there, which I'll later give a name to. But for now, you just see there's a sort of fundamental spine of this tree, and then there's a bunch of trees hanging off of it. And by the way, if you look from here in this direction, you can see this point. All right, that is visualizable because it does lie in this direction. You just have to make a turn, but that's okay. So when I say the set of all points you can see here, I mean I'm including all this stuff over here. But you can't see a point up there. Okay, now the tangent directions at the Gauss point, they correspond bijectively to elements of P1 of the residue field of K. And so the way to see this is that so the tangent space at the Gauss point, the set of tangent directions, those correspond to open disks of radius 1 contained in the closed unit disk. Plus there's this complement of the unit disk in the projective line, which you think of as an open disk around infinity. And so these tangent vectors sort of correspond to open disks whose closure, in some sense, is the corresponding closed disk. And there's an explicit way to see that using the terminology I've introduced. But the intuition is just this, that if I have a closed disk, say the unit disk, and I want to move in Berkovich space from there, how can I do it? I can either start increasing the radius, and that's kind of moving towards infinity, or I can start decreasing the radius. But if I decrease the radius, I have to specify in what direction I decrease towards. Because if I decrease towards 0 or 1, I get a different family of disks. But if I decrease towards 0 or some point very close to 0, periodically close to 0, then it doesn't matter. I'm sort of starting out in the same direction. So those will share the same initial segment. So what you see is that the open disks of radius 1 correspond to the different tangent directions in which you can move. And those clearly are sort of parameterized by the residue field. So more generally, for each type 2 point, the set of tangent directions is in bijection with P1 of the residue field, but it's not canonical. I mean, there's one direction going up and other directions corresponding to open disks of radius r. But if you want to put that in one-to-one correspondence with the residue field, you have to sort of choose some isomorphism that takes the disk of radius r to the unit disk. So anyway, the cardinality of the tangent space is like this. For points of type 2, as I just said, it has the cardinality of the residue field of K, which could be countable, but it could be uncountable. At a point of type 3, there's just two tangent directions, because there's no branching there. You can either increase the radius or decrease the radius, and that's all you can do. You can't move somehow, you can't decrease in different directions because there's no physical points on the boundary anymore, right? So somehow, when you have an irrational disk, you have less flexibility about how you can move within Berkovich space. And at a point of type 1 or type 4, those are endpoints of that tree, so there's only one direction you can go. And I want to finish up by just introducing some terminology that I'll use later on, which is, this was introduced by Rivera-Letellier. As I said, he sort of independently discovered Berkovich space, and actually what he constructed was isomorphic to this H-Berk, which is the complement of the set of points of type 1. It's all the new points you've added into Berkovich space. So I'll refer to that as Berkovich hyperbolic space. It's all the new points you've added in. And I'll have H-Berk-Q being the set of just type 2 points. H-Berk-R is the set of points of type 2 or 3. And I'll remind you later of this notation. The main thing I want to say is that there's a well-defined diameter of a point of Berkovich space, which is just the limit of the radii of these nested disks. And so in particular, if you have a point of type 2 or 3, which corresponds to a physical disk in K, the diameter is just the diameter or radius, same thing, of that disk. And But it makes sense for points of type 4 too. You can take the limit of the radii. And there's an intrinsic definition of the diameter, which is you take the infimum of the seminorms of t minus a over all a. And this agrees. So, but intuitively, it's just the radius of the corresponding disk. And because of this remark I already made, points of type 4 have positive diameter. And the points of diameter 0 are exactly the points of type 1. So this hyperbolic space, these are the points of positive diameter. And the reason that this comes in is that, well, there's a partial order on A1 defined just by saying that x is less than or equal to y if and only if, for every polynomial, the absolute value of f sub x is less than or equal to the absolute value of f sub y. And this is equivalent, in terms of disks, it just means that one disk is contained in the other. So the partial order just comes from containment of disks. And you can use your imagination to extend this to points of type 4. But in particular, any pair of points has a unique least upper bound. And this was when I was telling you the path structure. The path from x to y goes from x to the least upper bound of x and y, and then back down to y. And, right, so x wedge y, x vy is the point corresponding to the smallest disk containing x and y. And the main thing I want to sort of conclude with today is the existence of a canonical metric on Berkovich hyperbolic space. Because this is often not emphasized in the general theory of Berkovich spaces in analogy with rigid analysis, but it's very important for what I want to talk about in my lectures. Namely, if you have one point less than or equal to the other, so say imagine one disk contained in another disk, you just take the log of the ratio of their diameters and think of that as the length of the path from x to y. So if I just have one disk contained in another, I take the ratio of the two diameters, and the logarithm of that will be called the path distance. Right, so here I'm talking, right, it's ultimately going to be symmetric. So this is if x is less than or equal to y. And now, in general, I'm going to add the distance from x to x vy and then y to x vy. So it will really be, in terms of the tree structure, I sort of take the length of this path and then I add the length of that path going down, except the way I've defined it. I go up. So anyway, this gives a symmetric function of x and y. And you can check this is actually an ultrametric. It satisfies the ultrametric inequality, and it's actually a metric. And the log sub v is just some suitable normalization. So if k is Cp, then I just want to take logarithms to the base p, so that rather than getting some irrational numbers, my logarithms are like rational numbers. But since I haven't told you what k is in general, log sub v will just be some suitably normalized logarithm. And so the main point is that for one disk contained in another, this is just some very concrete thing, log of the big radius minus log of the small radius. The points of type 1 are infinitely far away because they have radius 0. So when you take the log, you get infinity. And that's why I'm restricting to hyperbolic space when I define this metric, because otherwise it's a singular metric. You have points at the boundary, the type 1 points, which are infinitely far away. And the crucial observation or crucial remark is that this metric topology is not the subspace topology. Okay, so I'm not saying that the Berkovich space is somehow always metrizable. That's not true. And even the H-Berk subspace is not, in general, metrizable. These two topologies are completely different. But it is true that the inclusion map is continuous with respect to the metric topology here and the Berkovich topology here. So they're not completely unrelated. But the other key point is that this metric that I just defined on hyperbolic space is canonical. It's completely canonical. And one, as I've stated it, it kind of seems to depend on choices of various coordinates. Because I took these disks, and if I took some Mobius transformation, who knows what happens. But in fact, it's a simple exercise to see that PGL2K acts via isometries on this Berkovich hyperbolic space. So if I move things around by some Mobius transformation, it acts by isometries with respect to the metric I just defined. And in particular, this allows you to show that this metric rho is canonical. And this will be very important later. So we've got this subspace H Berk, which has a canonical metric on it, but the metric topology is different. And I think this part, since I've already gone over time, I can basically run through very quickly because I won't need it, except in the last lecture, I think. But the usual distance, absolute value x minus y, does extend to Berkovich space, even though somehow you can't subtract 2 points of Berkovich space and take the absolute value. I mean, x minus y itself does not extend to Berkovich space, but the absolute value of x minus y does. Namely, you can take the diameter of the least upper bound of x and y, and if you think about what I've said, that sort of generalizes the distance between x and y. But it makes sense for all points of the Berkovich affine line. And I'll call this the canonical distance relative to infinity. And it, as I said, it generalizes the usual distance. And just intuitively what it is you're taking the soup among all representative points in one disk and all representative points in the other of the difference. So what is the canonical distance between two disks? It's just sort of the maximum distance between points of one disk and points of the other disk. So in particular, the canonical distance from a disk to itself is just the diameter of that disk. It's not 0. So the canonical distance is not actually a distance. It's not a metric. So it's admittedly bad terminology. So if you fix one variable, it's continuous. But as a function of two variables, it's just upper semi-continuous, which I don't have time to explain why that is. But it's kind of a key technical point when you're doing potential theory that it's unfortunately not actually continuous. So that causes some problems. And it does satisfy the ultrametric inequality, but it's not actually an ultrametric, because the distance from points of hyperbolic space to themselves is strictly positive. But that's the only axiom that you're missing. And I'll stop there. Thanks.
All right, so if there are one or two quick questions.
So the pictures that you've drawn, how good would these be for intuition if you were looking at Berkovich spaces more complicated than A1 and B1?
Are you asking about more general Berkovich spaces? Or, all right, so Jacob was asking about this picture that I drew. How good is the intuition you derive from that for other Berkovich spaces? So I'll describe Berkovich curves in some generality and how to think about them. So the intuition is quite good, except they're no longer trees. They might have some finite homology. So I'll explain that in detail later on. But in higher dimensions, well, it's probably not so good, the intuition you get from this picture. Because somehow, rather than being based on trees, it'll be some higher dimensional simplicial complexes that will build the space up. But actually visualizing how they're glued together and where they all lead to is something that I can't personally do. But I mean, in any case, in one dimension, it's pretty good, though. This gives you the right intuition in general, except you might have to allow some finite homology. The question is, if K is not algebraically closed, what is the right definition of a hyperbolic space? So I think probably the right, I think probably the right thing is to remove all of the rigid points, not just the K rational points. Okay, so rather than repeating that, I'll discuss that later and say something if I can summarize that in the next talk.